So we will be taking up the multinomial naive Bayes. Let's see what is multinomial naive Bayes, and then we will be seeing the Bernoulli naive Bayes, and then we will be comparing the two. So this is the problem set that we will be taking. So we earlier saw the multinomial naive Bayes algorithm. Now this algorithm is in the form of pseudocode here, and this is taken from the book by Christopher Manning, and this book is also available over the internet. You can go through and you will find the relevant content in that book also. So this is the first procedure is the training part. As you all know, we first extract the vocabulary, and then we have the vocabulary, that is V, and then we have is n is the number of documents. Then for each class C, we see that how many documents are present in that class. Alright, so this is in with respect to the text classification. Now going with the previous example, we will be counting for a particular class how many words are present in that particular class, right? So this NC is the count of that particular identity or that particular document or the particular word in that class, right? So count of documents in class D is we will be counting how many documents are present in the class C. So here we see that we are having 3 documents in the class C. Alright, so this is 3, and there is in another class we have 1 document, right? So NC is the count of number of documents in a particular class C, and N is the total number of documents. So for a particular class C, the probability of a given document will be NC upon N, right, which we can call the prior probability P of C as NC upon C, or more specifically you can write this as P of class is equal to C is equal to NC upon N, and if P of class C is equal to J, that is equal to Nj upon N. So in our case this is 3 and total documents are 4, and this is 1 and total documents are 4. So these are the prior probabilities, right? So we calculate the prior for each class. So this statement is calculating the prior. So the next is again the text of class C is actually again we are collecting all the documents that are present in a particular class C. So we will be now looking collectively in this part, so because this part belongs to the class C, so we will be collectively looking up on this part only, right? So when we are binarizing multinomial, so the updated corpus is looking like this. The updated corpus is this. So each of these Chinese, the count is now reduced to 1, and the Beijing is already 1. Similarly in the second document the Chinese count is reduced to 1, and the third one does not change. So in this way what we do is that we are collecting this piece of text for the class C and this piece of text for class J for calculating the class conditional probabilities. Right, so we all know that while calculating the conditional probability, we do just look at that particular portion of the class on which we condition it. So now for each term that belongs to vocabulary, so total count of the term will be the count of the term in the particular class text, right? So this we will be counting for each. We are having the vocabulary as the Chinese, then Beijing, then Shanghai, then Macau. So these these are the just vocabulary for this particular class. So for each vocabulary we will see, and we have these also Tokyo, Japan also. So for each vocabulary we will see whether that particular term is present in the particular text of that class or not, and if it is present, we need to calculate the count. We need to calculate the count of the tokens of that term, right? So we need to count the tokens of that term. So in normal multinomial naive Bayes, we will be just counting how many times the Chinese have occurred. So this, which is 1, 2, 3 and 4, 5. So in this case, the count of Chinese or n, or this t of Chinese is equal to 5. But in case of binarized, we see that the term is only once. So the count of this t Chinese comma c will be equal to 3 only, right? So this is the binarized multinomial naive Bayes. So in general case, this same algorithm will work, but what we have done is that we have just changed the corpus, and then we are giving new corpus to the same multinomial naive Bayes algorithm. Or otherwise, if we want to change in algorithm, we will see whether this conditional probability, if it is non-zero, we will just make it 1. So we will apply some condition here. If conditional probability is not equal to 0, that means it is non-zero, or it's greater than 0, it's positive, then we make it as conditional probability is equal to 1. Sorry, we don't make it in the conditional probability, we just change the TCT here. Sorry, this is if the count is t greater than 0, then we make it as TCT as 1, right? So every time when it will count more than 1, so it will just turn it into 1. So we can here change the algorithm also, right? So in this way we will be able to calculate the conditional probability for each term present in the class C, right? And then we can apply the Laplace smoothing here. So we are adding here we are adding 1 to the count, and we are adding 1 to all the vocabulary, that is t of CT dash is total number of terms present, and we are adding 1 to each term. So that is the total plus n plus v, and this is t of CT. So in this way we can calculate the conditional probabilities, right? And we know while predicting or while testing, so we need to again extract the tokens from the test document, and then for each class C we again calculate the score with the help of priors, right? So since we are having the log probabilities here, so we are just assigning the score of class C as log prior of C plus the conditional probability of TC, right? So whatever number of terms is present in this particular document, it will be adding all those. So this will be for all those terms only that are present within the document, right? And then we can apply this argmax on the score, right? So this is actually the binarized multinomial naive Bayes, right, in which we are saying that whether a term is present in the particular document or not, right? So in this document, the Beijing is not present, so the count of Beijing is 0, right? So if we calculate the count of Beijing in class C, the count of Beijing is only 1. Similarly, the count of Shanghai is only 1, the count of Macau is only 1, right? So what will be the probabilities? The probabilities will be 1 is the count of Beijing plus Laplace smoothing divided by total number of documents is 3 plus total number of vocabulary here is 6, right? So this is the probability of Beijing given class C, right? So in this way we can calculate all the probabilities and apply it into this here, and then calculate the score of all the classes, and then apply the argmax and find out that particular class which is having the highest score. Now what is actually the Bernoulli naive Bayes? Bernoulli is also very, very similar to this. What is the similarity here is that when we say naive Bayes or any text classification algorithm, we are assuming that these are the sequence of words, right? So we have this word 0, word 1, word 2, word 3, dot dot dot, word k, and then we have these documents. This is document 1, this is document 2, this is document 3, and we have p number of documents here, right? So we see in multinomial naive Bayes whether this word is present here or not, and if it is present on this position, we would like to place the count of that particular word. So the count is, suppose one word 0 is present 4 times in document 1. Similarly, we would like to see that word 1 is present suppose 7 times in the document 1, word 2 is not present in the document 1, and word 3 is suppose twice present in the document 1, and word k is suppose it's present suppose it's not present in the document 1, right? So in this way we can have the counts of all these documents, and then we can apply the Laplace smoothing and then calculate the probabilities. So when we binarize it, we say that we are not making it we are not taking the whole count, but we are just seeing whether the word 0 is present in the document or not. So we are just writing 1 in place of 4, we are writing 1 in place of 7, and 0 remains the same. We are writing again 1 in place of 2, and the 0 remains the same, right? So in this way we get this kind of matrix, feature matrix. So this is 1 1 0 1 and 0, right? So we are calculating the probability p of word given a class as count of word in all the documents of class C divided by total number of words. Right. So the count of all words, count of the word in all the documents of class C. So we will be looking at the count in this way. Right. So this maybe somewhere. Let's look up this one, 0 1 1 0. Right. So we will get the probability. Right. but in case of Bernoulli Bayes, we apply the Bernoulli distribution, and the Bernoulli distribution says that if word is present, then probability is P, otherwise it is 1 minus P. Right. So now this we see that if the word is present, the probability is P, whatever we are calculating, but if it is not present, the probability is 1 minus P. So this is actually the difference with the Bernoulli and the multinomial. We are marking all the zero, these zero counts are also generating some kind of probabilities, right? So when we change this algorithm to Bernoulli naive Bayes, we see that we have all the things are same here. Instead we calculate the class conditional probability with the help of this formula. In the previous case we had this TC and NC is actually the same thing. So we have the number of count of word in all the documents of class C divided by total number of words. So this is actually again the same thing, count of the term T in class C divided by the total number of words in that class C. This one is the again Laplace of smoothing in the numerator, but we see that we are having only two options to choose, so that's why we are adding here 2, right? So this is actually the characteristic of Bernoulli distribution, which says that Bernoulli P for a given random variable x, if x is equal to 0, then the probability is P, and else probability is, sorry, this is for x is equal to 1, the probability is P, and for x is equal to 0, the probability is 1 minus P, right? So the word has only two options here. It can either be present or it can be absent, right? So here we see that in the Bernoulli case, either it will be a 0 or it will be a 1, right? There are only two options given by the distribution itself, that whether it can be present or it can be not, right? So we can take an example of the flipping of a coin, that when we flip a coin we have only two options left out, whether it can be head or tail. So it's that kind of scenario and that kind of distribution that has been applied to the algorithm. So we are having only two options present here that can be chosen by the word. So we are dividing the numerator, we are adding 2 in the numerator here, right? So that's why this formula is NCT plus 1 divided by NC plus 2. Similarly, we have the same thing in all this testing part, but the score is calculated when the term is present. The score is calculated as the log conditional probability T. You see here it's the same as the log of conditional probability T term in the given class C, but if the term is not present, we specify that the probability is 1 minus P, right? So the probability is 1 minus conditional probability, right? So this generates the probabilities. It generates the probability of words that are not present in class. As well, right? So when we calculate these probabilities, we see that the Chinese is present in 3 documents, and there are 3 documents in total. So we add 1 in the numerator, we add 2 in the denominator, and in this way we can calculate all the class conditional probabilities, right? And for a new given document, we can again calculate the probabilities P of Chinese given C, right? P of Japan given C, and P of Tokyo given C. These 3 words are present in the document, but this Beijing is not present in the document, so I am applying 1 minus P of Beijing given C. Then this Shanghai is again not present in the document. This probability is again being applied in calculation, and then P of Macau given C is also not present in the document. So we see that these 3 probabilities are those probabilities of is the probability of those words these are which are not present, right? So the probability of those words which are not present in class C, right? So you see that we are having this, the final calculated probability is 0.005 for class C, and for class C naught or class J, the another class, we are having 0.022, right? So this class C naught or class J is the predicted class, right? So we can see from here also, due to the presence of these Tokyo and Japan, right? So we are getting Tokyo, Japan and Chinese, we are getting some probabilities. Sorry, for this one, Chinese, Tokyo, Japan, Chinese, Tokyo, Japan. For this document, we are getting the probability of Chinese, we are getting the probability of Tokyo, we are getting the probability of Japan, as well as we are multiplying the probability of Beijing, we are multiplying the probability of Shanghai, and we are multiplying with the probability of Macau, right? So now, what is the problem with this Bernoulli knife base? The problem with the Bernoulli knife base is that if even this weight or the count of document is very low, then also it will be taken into consideration. If the count of the word is very high, then also it is taken into consideration with the same weight, right? If it is 40 or 400, then also it is considered as 1, and if it is a small value, from 1 2 3 4, then also it is considered as 1, right? So that's why this Bernoulli knife base is not a very good algorithm for text classification, right? So whenever we calculate the probability of a term of a word given a class, it is actually the fraction of the class C that contains the term T, right? But in case of multinomial knife base, we are not going through the fraction of the documents, but we are going through the positions on which these are present or not, right? So we are just checking by the positions. So in Bernoulli knife base we are looking by this way, but in case of multinomial knife base we are looking this way, right? So it is actually the fraction of tokens in the document of class C that contain the term T, or in the other words we say it like that: fraction of positions in the document of class C that contain the term T, right? So the Bernoulli is fraction of documents of class C that contain the term T, and multinomial is fraction of tokens of class C that contain the term T, right? So in this way we are looking the fraction of documents, and in this way we are looking at the fraction of tokens or collection of words, right? So in this algorithm, this is actually, again, the formula is almost same. This is actually the fraction in which the fraction of documents in which the term is present, and this is the fraction of, again, collectively the documents in which the term is present, or the fraction of tokens in respect of total number of tokens, right? So that's why we apply a n here, that is total number of tokens that are present here, and this is the total number of documents that are present here, right? So this is actually the little difference. We calculate the probability in Bernoulli Naive on the basis of number of documents, and in the multinomial Naive we calculate on the basis of tokens, right? So this probability is amount of or fraction of tokens in respect of total number of tokens, right? And this probability is number of documents in which the word is present divided by the total number of documents, right? So Bernoulli is actually a binary occurrence model, right? It ignores the occurrences of, let's write it somewhere. So number one point is Bernoulli, let's write here multinomial. So Bernoulli calculates the probability of a term or a word given C as fraction of documents of class C that contains term T, right? So we are just seeing whether in that particular document the term T is present or not. But in this case, P of T given C is equal to fraction of tokens in class C that contains term T, right? So let's again see here. This is the corpus, this is the class C, and these are the term T, right? And there are other terms also, T dash, T dash, T dash, T1 and T1. So this is actually the collection of terms T, the fraction of terms T that are present in this class, right? But here we just look up in the individual documents, in each document, whether T is present or not, right? So this is the class C. We will see whether T is there or not, T is there or not, like this, right? So here in multinomial we take out all the calculate in respect of terms, and in Bernoulli we calculate in respect of the documents. The second point is that this is a binary occurrence model. This is the multiple occurrence model. So Bernoulli may make mistakes, right, in long documents, so not performs well for long documents. And performs well for long documents. Right, so these are some kind of primary differences, basic differences between the two types of algorithm. Right? And one more difference is that probability of term not present in the test document is also non-zero and equal to 1 minus p of term given c, right? And this is probability of term not present in the test document is not taken into consideration. Okay, so we just don't take it into consideration. So we just don't take these probabilities into consideration while calculating. We are having just only p of c dot p of Chinese given c dot p of Japan given c dot p of Tokyo given c in case of multinomial libraries. Right. So when the document is too long, the problem will be that it's only just for the probability of single count of Chinese and the probability of large count of Chinese will be the same. Right. So it means that whether it means the presence of Chinese or large presence of Chinese or low presence of Chinese will not be considered in this Bernoulli libraries. Right. So that's all on the part of multinomial and Bernoulli libraries. So if you have any questions, you can ask. Then we will take up the next topic.